country's energy comes from the following sources. 60% of it comes from a natural gas plant with an average efficiency of 30%, and 40% of the electric energy comes from coal plants having an average tested heat rate of 11,000 BTU per kilowatt hour. If the current demand is 25 megawatts, estimate how much total input energy will be used over the next 50 years. Assume a continuous exponential growth model at 1% per year and a constant percent mix of generation. So the givens is that we have the energy output from the natural gas plant is equal to 0.6 times the total energy output, and the energy output from the coal plants is equal to 0.4 times the total. That's just a mathematical way of saying the output is 60% of the total for natural gas and the output is 40% of the total for coal. We were told that the efficiency of the natural gas was 30%, and we were given a heat rate for the coal, and that was 11,000 BTU per kWh. We were also told current demand. Remember, demand is a power. P0 equals 25 megawatts. And we're asked over a 50-year period, so T is 50 years. And we were told that the growth rate was exponential, continuous exponential, and it was 1% per year, which would write like that. We were asked to find the total input energy that goes into the two fuel plants. So basically the question is, we've got some E in from a natural gas plant. It goes into the natural gas plant, which has some efficiency. E out, that's electrical output energy. We've got another plant that's E in coal, that's the energy of the input coal. That plant's going to have some sort of efficiency rating. It's going to have its output, so the total output is going to be E it's just the two of those added together, right? Those are the two sources of energy, the natural gas plants and the coal plants. And what we're being actually asked to calculate is what these numbers are together, E in total. So I need to calculate that, and I need to calculate that, and I need to add them together to get the total input energy. The reason we need this is because we know we can calculate this number here from the growth model, and we know that this is 60% of this number, and this is 40% of that number. So how do we get this E out total? Well, remember that comes from our growth model. If we have a demand plot that looks something like this for an exponential model, we're saying, okay, we want to come out 50 years. That was the time period we're looking at. So the T here, we're looking at 50 in years. And then remember, this is a power, since it is a demand plot, that's in watts, and so this is 25 mega, or 25 e to the 6. And remember, if we integrate this, we get total energy used over that time period. And we've done that a couple times now. We know that the energy total electrical energy used is going to be P0 divided by alpha times e to the alpha t minus 1. And so we get E total is equal to 25 e to the 6 watts over alpha, which is 0.01 per year, and then e to the alpha t, so 0.01, I'm going to write that as per year here, and then times 50 years. So I want to just make a quick point about, I've made a lot of to-do about keeping track of units, and in this problem it's important. It's always important, but it'll really get you in this problem. Notice that when we do this calculation, in the exponent we've got 0.01 per year times 50 years, so the years are going to cancel, which is important because we're doing we're raising this to the power. So we're taking e to that, and we don't want a unit up there. So that leaves only the units over here, watts divided by something per year. So this year is going to flip up into the numerator, and my end unit, it's very important to notice that that's going to be watt years. So E total, if I do that math, gives us 1.6218 times 10 to the 9th watt years. Okay. So that's how much total energy I'll use over the 50-year period, based on integrating this plot here. Now part of that's going to come from natural gas, part of that's going to come from coal. We were given those fractions in the problem statement as 60% and 30%. So we can say the output energy from the natural gas plant is just 0.6 E total. So that's 0.6 times 1.6218 times 10 to the 19th watt years. And so that's going to give me 9.73082 times 10 to the 8th watt year. And then I've got E out in coal. That's got to be the rest of it because there's only two sources in this fictitious power system. It was 40% of the total, so I can multiply by 0.4 or I could do a subtraction. Both will work. I'm going to do the multiplication just because that's how my brain thinks. Why'd that happen? Okay. So we do that multiplication and you get 6.48721 times 10 to the 8th watt years. And so those are the outputs. We were actually asked to calculate input, and that's where we're going to go back to these formulas based on efficiency. The natural gas was that we had an efficiency of 30%, so E in, the input fuel energy in natural gas, is the output electrical energy in natural gas divided by the efficiency of the plant. We were given that directly, so we're just going to take this number here for the E out, 9.73082 times 10 to the 8th watt years. I need to divide that by 0.3. So that's going to give me 3.24361 times 10 to the 9th watt years. Then I want to know what E in coal is. The problem is I wasn't given this number here for coal. I was given heat rate. And so before we can calculate this, we need to convert the heat rate over to a efficiency. So I'll just put a colon here because we're going to do a little bit of math. So we know that the efficiency of coal, we can convert a heat rate to efficiency by taking the BTU content of a kWh, which is 3,412 BTU per kWh, and we divide that by the actual amount of energy that it took, which in this case was 11,000, the heat rate. So what a heat rate says is it took 11,000 input fuel energies to produce 3,412 output fuel energies. So that's equivalent to a 31% efficiency in the coal system. So that means the EN in coal is this number here, the output electrical energy from the coal plant, 6.48721 times 10 to the 8th watt years, divided by the efficiency of 31%. You'll get 2.09265 times 10 to the 9th watt years. So that's how much input fuel was needed in natural gas. That's how much input fuel was needed in coal. If I add the two together, as I indicated I would do at the very beginning, you find that the total input energy is 5.33626 e to the 9th watt years. And I didn't specify what units to put this problem in, so I'm going to leave it in watt years. Make my life a little easier at least.